time for this before the break? I think we do. Yeah, this is good. This is good. This will be perfect. I see what you're saying now. I need like a Vanna White to help me out. Or sunglasses. I've got a sweet pair. I'll bring them next time. All right. So, what we're going to do here is share with you this, not that, we'll do that later. I need Monty Hall, which is obviously I haven't opened yet. Monty, where are you? There you are. Okay, this is going to look a little weird at first, but I want you to kind of bear with it. This is one of the most exciting, I think, one of the most exciting applications of computer-aided mathematics in the world today. How many of you have ever heard of a flight simulator for training pilots? Flight simulator? Right. The idea of a flight, what is the idea of a flight simulator?
Simulated flight. Without crashing a real plane.
Good. Without crashing a real plane, you can still get the practice of flying a plane. So how do they simulate the flight? How is the flight simulated? Visually? Good. How else?
Oh, they move stuff at you.
Mm-hmm. If you get into like basically like what the seats look like in the cockpit, they move around quite a bit. What? I saw a couple of you went like this. What makes that happen?
Seats move around.
Right. What makes the seat move around?
I don't know, mechanics.
Mechanics? So what makes the mechanics say move the seat around?
Computers.
What is the computer saying? I love this. What the computer is doing, and this is why we have computers, the computer is essentially rolling lots and lots and lots of dice. More on this today. It's rolling lots and lots and lots of dice. For example, you might know, and I'm going to make this, and any pilots in here, I apologize for the crudity of what I'm about to say. Let's say that 5% of the time, on average, excessive turbulence is experienced in flight at 35,000 feet. I'm making this number up because I have no idea what that number actually is. So what the computer does is, it rolls dice from 1 to 100. If the number 1, 2, 3, 4, or 5 comes up, it shakes the cockpit. If the number 6 through 100 comes up, it doesn't shake the cockpit. Does that make sense? It's the same thing my TI is doing, but it's randomly generating numbers 100 at a time, or 1 at a time, from 1 to 100. If 1, 2, 3, 4, or 5, or 5% of the dice possible come up, it's going to say, okay, shake the cockpit, simulate turbulence right now. Every single method of what goes on in a plane cockpit is simulated by one of these quote-unquote die rolls. That's what's going on in flight simulations. Random, pseudo-random, if you will, events coming at you, governed by real laws. That's what I'm going to simulate right now. It's not quite as awesome as a flight simulator in an airplane or helicopter.
So the room's not going to shake.
But the room's not going to shake, I apologize. But what you are going to see let me walk you through the sheet. This up here is just keeping track of how many trials we actually run. So we've only run, I think, like 7 or 8 trials as a class. This is going to run like a few thousand for us very, very quickly. This is going to randomly pick a door between 1 and 3. Between 1 and 3, which is what you guys did, right? You chose, I'm guessing you chose kind of at random. You pick 1, 2, and 3, or 2. Okay? Beautiful, beautiful, beautiful. This is going to pick the door that Monty shows you. That formula's a little much up there. And the reason it's a little much is because there's 2 cases. This is what I was trying to imply, Amy, when you said 50%. What door I show you is dependent on whether or not you got the lollipop. If you got a wrong door, if you picked the wrong door, my choice is easy. If you pick door number 3, and the lollipop is behind door number 2, what door am I going to show you? I have to show you 1, don't I? But if you pick door number 3, and it was behind door number 3, which door am I going to show you?
Random.
2 or 1, and I have to randomly decide which one of those 2 to show you. That was tricky. I wasn't doing a very good job of random. I think I always picked the one on the right, or whatever one my eyes were looking at, I guess. The switch.
You picked number 2 whenever you could, it seems.
Not a robot. I am not. A robot I am not. Dr. Seuss up here. The switch is dependent also. This is your switch. Whether you decide to switch or not is based on randomness, 1 or 0. And the result just depends on whether your switch puts you on the door with the lollipop in it. So basically, as I hold down F9, we're playing this game over and over again. So see these little boxes up here? These are the same boxes we had. I'm going to go ahead and let this thing hold down with my stapler. Hang on, let me find my stapler. And I want you guys to watch what happens as I do this. Oh, there you are. Let's see if I can pull this off. Is that going?
It was.
No.
There you go.
It's not letting me let go. I was told that. Crazy. Now, what do you know What do you notice about the numbers that are popping up in that chart up there?
The people,
Say that again, Scotty.
the people that switch are actually having a greater chance of winning at the same proportion as the people who stay are losing. It's inverse.
Yes.
Mm-hmm. It very much is. I put the percentages down here. Do these look familiar to you guys? 0.33, 0.67. Do those look familiar to you from the 2/3 and 1/3 before? Yes, what Scotty just said is 100% correct. The people that switch are essentially twice as likely to win as the people that don't switch.
That's wild.
It is totally wild, but it's explainable using the methods of the way the game is set up. I love the 50-50 argument because there are two outcomes at that point, the door you have and the door you don't have. But those two are not equally weighted. You're seeing a simulation of it right now. Now some of you still might not be buying this. You might look at this and go, okay, I can see that your Excel is telling me 2/3, 1/3, 1/3, 2/3. So these numbers right here are essentially matching each other, and these numbers right here are essentially matching each other. So you stay, you win half the time as when you switch. If you stay, you lose twice the time as when you switch. So it is possible to switch and lose, but it's twice as possible to stay and lose. Does that verbalization make sense with the numbers we're seeing right here? But some of you probably still aren't buying this. You're probably still saying, okay, I hear what you're saying, but I don't buy it. So this is what I like to call empirical probability. We'll come back into this after the break. I want to shut this down real quick and return back to this guy right here and see if I can explain it less empirically and more case-by-caseally, if that's even it's not a word, I made it up. So here is what I like to call a contingency table. More on this when we play with statistics. Do you agree that there are 9 things that can happen when you play this game? You pick one of 3 doors, and the lollipop is behind one of 3 doors. And sometimes you pick the door it's behind, and sometimes you don't. So, if you pick door number 1, and the lollipop is behind door number 1, and you stay, well, that's a good thing, isn't it? That's a good thing. That means you picked the door it was behind, and you stayed with that door. So you're going to win in that case. But if you pick door number 1 and stay with door number 1, and the prize is actually behind door number 2, you're going to lose, aren't you? You're going to lose. You're also going to lose if it was behind door number 3. So you see how this column right here has 3 elements in it? 2 of them are lose and 1 of them is win? Every column where you stay has 1 win and 2 loses. Because the only way you're going to win if you stay is if you landed on the door a lollipop is behind. And how often do you land on the door a lollipop is behind? 1/3 of the time. Does that make sense? So the only way that staying is a good strategy for you is if you pick the right door off the bat, which only happens 1/3 of the time. Does that make sense, Gabe?
Yeah, but it's like, how are you, like, I don't know.
No, keep thinking, brother. Look at this.
I get exactly what you're saying.
You still get, okay.
But you're saying, like, you're better off staying if you pick the right door? But
Yeah, but how often are you going to do?
Yeah.
All I'm saying, no, think about what I said. I didn't say that. I said the only way you can guarantee a win by staying is if you pick the correct door,
Yeah.
which only happens 1/3 of the time.
Yeah.
But look what happens when you switch. When you switch, every column of the door you picked is 2/3 win to lose, because the only way you lose in this case is if you got the right door in the beginning. But did you most likely get the right door in the beginning? No, you were twice as likely not to. So it does pay to do what in this game?
Switch.
Yes, you're going to win twice as often as you lose in this game if you switch.
Yeah, it only works if they open one door and show you.
Yes, Cheryl, that's the kicker. The kicker is opening that door helpful to us? Hell yeah, it is, because he's taking all that probability that was unknown there and putting it into the other door. It was 1/3, 1/3, and 1/3. When he opens the door, it becomes 1/3 and 2/3. It's still 100% probability that the lollipop is somewhere behind that door. When he opens that door over there, he removes the likelihood that that door was even there in the first place. But it's not 1 and 2. Your door is still only right 1/3 of the time. That means the other door that you don't see is right 2/3 of the time. It's definitely helpful to have that door open. This, in case you're not buying that, try this. Okay, let's pretend this time there are 10 doors. If you're buying my whole argument, that's good. If you're not buying my argument, Pretend there are now 10 doors. Same game though. Same game. Same game. There's one prize behind one of the doors, and you pick door number 5. I put WLOG for without loss of generality. That means it doesn't matter what door you pick. The same argument applies to all 10 of them. With me so far? You pick door number 5. Monty does this. Are you going to stay with the door you picked, or are you going to switch to door number 9? A vote for switch? A second for switch? A vote for switch? Your call, friends. Your call. A vote for switch? Go switch, switch, switch. Switch. Chris says switch. Yes. Chris says switch. Sydney's agreeing. Switch. Yes. You're going to stay. So, now, let's talk about the likelihood of us winning this game. When you first saw 10 doors, we picked door number 5. What's the chance the prize is behind door number 5?
1 in 10.
1 in 10. Just like it was 1 in 3 with 3 doors, now it's 1 in 10. Fair? 1 in 10. 1 in 10. What's the chance the prize is over here? 1 in 10? 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 Okay, beautiful. So there's a 100% chance distributed equally amongst the 10 doors. Now I'm going to stop this for a second, okay? And I'm going to go through this one slide at a time. When Monty opens that first door, what's the chance your lollipop is behind this door again? Remind me again. It's still 1 in 10 because it didn't move. The other 90% is still amongst all the other doors that are still unknown, but there's now nothing attached to this door. It's almost like that door didn't even exist in the first place, which means each of these remaining doors is how likely to have a lollipop behind it. What's 90 divided by 8? That's the likelihood. 12.5%? Is that roughly 12.5%? Whatever 90 divided by 8 is, right? 90 divided by 8. 11.25%. Your door is still at 10% because you're only right 1 in 10 times. But the other 90% is spread amongst the other doors. By taking this door away, it's as if the door was never there in the first place. But there still has to be 90%, which means the other 90% is split. Then he opens one more. How much probability is now behind each of these other doors? What's 90 divided by 7? It just went up, didn't it? Each of these doors now has 90 divided by 7 or 13? 12.8, 13%. Call it 13%. Each of those doors is 13% likely to have a lollipop. What's 90 divided by 4? 22.5%. Remember, your door is still at 10% because the pop did not move. The pop is in the other doors 90% of the time. So if this one is only 10% of the time, if I equally spread that 90% amongst the other doors, it's got to keep going up for each door. So now we're down to 1, 2, 3, 4, 5, 6 doors. 90 divided by 6 is, I can't do it in my head right now. Thank you, 15%? Yeah. How about 90 divided by 5? 18%. Now each door is 18%, I believe. Now it's 90 divided by 4, 22.5%. Now it's 90 divided by 3, 30%. 90 divided by 2, 45%. And finally, when you're down to here, that door has 10% of all the pops in it over time, which means that door has 90% of the lollipops over time. So would you switch? Yeah. Hell yeah, you would. For the same reason you switch with 3. It's just more obvious with 10. Kate?
I still don't see how this is working, how you divide the 90 by the others.
Think of it this way, my friend. Think of it this way. Let me back up again. That's a great question, by the way. Kate's question is fantastic. She says, wait a minute, I don't understand why you're dividing up the 90 by the number of doors. Here's the deal. When you pick the door here, you're 10% correct.
Yes.
That means there's a 90% chance the lollipop is in one of these doors over here.
Yes, but should the 10% go up when you...
No, because we didn't move the lollipop. You were only 10% right in the beginning. You will always only be 10% correct in the beginning. So when Monty opens all of those doors, that door is still 10% correct. All these other 9 doors are still 90% correct. What's the chance the lollipop is behind this door now that it's open? 0. What's the chance it's behind that door now that it's open? 0. 0, 0, 0, 0, 0, 0. So all those zeros plus that door have to represent the 90% that's left. which means that door over there has to be the 90%. Kate, you buy that? Ish?
I'll just take your word for it.
Ah,
I'm getting this.
for now, you can do that. That's totally fine. I encourage you. This will probably work on the back of your mind. I will tell you when this made sense to me. It did not make sense to me the first time I read it in class or was told to. I never actually saw this in class. I read it in a journal. I was trail running through Brandywine Creek State Park back in Delaware. And it was funny because I was just there about 3 months ago, and I went for a trail run on the same exact trail. I ran by the exact same tree when it hit me, and it made sense. So of course, being a 2013 guy, I took a picture of it on Instagram. Ah, yes, the elm tree that I ran by when I first understood the money. Oh, yes, all the same post. But that's it. Your brain, if it's not getting this right now, these are the jokes, kids. These are the jokes. If your brain's not processing this right now, don't worry. Let it work on it. If you're getting it right now, Gabe, like I saw your face change, you went, I got this now. I know what you're talking about. Awesome. If you're not convinced yet, let your brain kind of mull over, and it will work on it whether or not you want it to. The subconscious works that way. Happened to me, Brandywine Creek State Park, in the middle of twisting my ankle in rock garden beds and whatnot. It came to me like that. So let's take.